Thank you very much. So we're going to get rid of the light to start with. Okay. Thank you very much. Thank you for all coming out on this bright, although crisp morning to hear something about science and what we do in my laboratory. Mostly about science. I'm not going to talk so much about exactly what we do in our laboratory, but things are going to be related. So what I really want to talk to you today is about light and about how light interacts with molecules and how we can learn something about molecules from those interactions. I've given you here my email address should you have any questions or wish to contact me later. But of course, in anything we do here at Yale, in research and teaching, it's not really only the professors that matter, right? It's also the support that we have. And in particular, doing research, I'm very fortunate to have a wonderful group of students who actually do the experiments because I can barely see things at my age nowadays, actually. And so you'll see some of my students sitting in the front rows here. They'll wave. They're going to do some of the demonstrations that I'll show you today. And what we do in my laboratory can be classified as molecular spectroscopy. So it's going to involve molecules, and it's going to involve spectra, which is what is basically the interaction between light and molecules. So let's talk a little bit about how I became a scientist, where I came from, and my motivations. I was born about 150 miles from New Haven in New Jersey, the Jersey coast. Small town, less than 1,000 people, Allenhurst, New Jersey. I like to call this the real Jersey Shore, right? Not like the television show that young people should not be watching, clearly. And so my family are not scientists, but they were very accommodating when I started taking televisions apart and all sorts of things apart to quote unquote improve them, and never got them back together. So I was always very interested in how things work, how objects are put together. And so that really piqued my interest in science, and I must say I had also very supportive teachers, in particular my 7th and 8th grade science teacher, Mrs. Houlihan, really was instrumental in encouraging me to do science. So I went to high school in a neighboring town. The neighboring town is Asbury Park. Okay, Asbury Park, some of you might recognize the name. So I went to Asbury Park High School, neighboring town, and at the time I went to high school, the mid-70s, Asbury Park was becoming the destination for rock and roll. There's something called the Jersey Shore Sound, which combines rock and roll with rhythm and blues. And you know, when I was growing up, literally this guy, Bruce Springsteen, was a youngster, wasn't really known yet, and I got to see him certainly in concert when nobody knew who he was, right? But in 1973, he did come out with this album, all right, Greetings from Asbury Park, New Jersey. So when I was in high school, I was very interested in photography, okay? So photography actually, you know, optics, light, that makes sense with what I do nowadays. But let's understand, photography for many of you today, you know, you take your cell phone, you take a picture, you hook it into your computer, and the picture comes out. Photography back then, no computers, right? Photography, you took a picture on actual film, you had to develop the film, you had to make a print, so a lot of chemistry was involved, right? So I got interested in optics, I got interested in chemistry, how do you make prints, how do you make pictures, right? And I took that with me to college. In college, I took my first chemistry class, which was actually given by a Nobel laureate, and I was totally caught, right? I was totally interested in chemistry. As Kurt Zilm indicated at the beginning, I started out doing research as an organic chemist, and that organic chemist had actually a collaboration with a physical chemist using lasers, and that's how my path got steered into optics and lasers. So I'm a physical chemist. Let's understand what a physical chemist is. So first of all, chemistry. What is physical chemistry? Well, chemistry we like to call the central science. We like to call it that because chemistry is a physical science, but it actually joins the biological sciences or applied sciences, so medicine and engineering, with the physical sciences, physics, mathematics, and everything. Chemistry is at the core. Chemistry really involves anything having atoms and molecules in it. So physical chemistry, what is physical chemistry? Well, if you go and look it up in a dictionary, you get this. A branch of science applying physical methods and theory to the study of chemical systems. And this is true. We take ideas from physics, we steal them, right? And we apply them to try to understand chemical problems. But this definition is boring, right? So we prefer a much different definition, first stated by a very famous physical chemist, G.N. Lewis. And G.N. Lewis defined physical chemistry as being anything that's interesting. And that's how I like to think about physical chemistry. We take tools, often developed by other disciplines, and we apply them to try to understand chemical problems. And oftentimes we improve and refine those tools to make them do things people haven't been able to do before. So in this talk, I'm going to tell you about something interesting. I'm going to tell you about spectroscopy. So let's think a little bit about spectroscopy. Fundamentally, spectroscopy is the interaction of light with matter. So light here means electromagnetic radiation. We're going to have to talk a little about what we mean by electromagnetic radiation. And matter means literally atoms and molecules. And so there are many forms of molecular spectroscopy. I have these various cartoons. We'll touch on various aspects of these cartoons throughout the talk. So let me give you a history. And this is a very abridged, very brief, and a very much biased towards my opinion history of what I would call quantitative spectroscopy. And we have some demos that are going to go along with this. So my first bullet point here is Isaac Newton. Isaac Newton in 1666 showed, and it's sort of indicated in this picture, that you could take sunlight, pass it through a prism, and disperse it into the colors of the spectrum. Okay? And so we have, and this led him to conclude that color is an intrinsic property of light. And so we have a demonstration of this over here that my student Paul is going to show you. We're going to plug it in. And here you see what we would call white light. It's not sunlight, but we'll agree that's white light. We pass it through a prism. This is not quite the prism that Isaac Newton used, although it looks that old. But it's a prism that actually has more ability to separate the light into colors than the one Isaac Newton had. And you can see the white light passes through the prism, and it comes out in the colors of the rainbow. And it's a continuous change in color, ranging from red through orange to yellow, green, blue, indigo, and violet. So we can take white light, separate it into the colors of the spectrum. So Isaac Newton did this in 1666. He also had some ideas about what is light. Oh, sorry.
We learned about Isaac Newton yesterday.
You did?
I'm not kidding.
What did you learn about him?
We learned that basically we were learning science and we were doing gravity. So like Isaac Newton, in this passage, it says that Isaac Newton got an idea about gravity when he was in his garden drinking tea or whatever, and then
An apple fell on him. Yep. So Isaac Newton is known for many things. He's was a very great scientist, certainly known for gravity, certainly known for mechanics, how things move, also known for developing calculus, also thinking about light, and even he was a chemist. Those are secret things that he never told anybody. He was an alchemist. He was trying to turn lead into gold, right? So he did many, many things, many, many things. But Isaac Newton also argued that light is composed of little particles. And what happens is as the particles pass through something like a prism, a denser medium, they're bent or diffracted. This was not the popular theory at the time where, as we'll see, light was considered to be waves. But several hundred years later, at the beginning of the 1900s, we'll also talk about our modern idea of light is that it is particles, at least under certain circumstances. So that's our first bullet, Isaac Newton, 1666, who used the prism to disperse sunlight. My next very biased bullet is Fraunhofer. Joseph von Fraunhofer in 1814. He developed something that replaces a prism, something I hope you all have one of when you first came in, this little diffraction grating, this little slide that doesn't use a prism to separate the colors of light, but it actually uses a process we call diffraction that we'll talk about a little bit later. And he looked at the sun, looked at the spectrum of solar light, and what he found is that he didn't only see the continuous colors I showed you here, but he also found many, many dark bands appearing in the spectrum. This is a modern version of what Fraunhofer saw. And what I'm showing you here is a band going across. It then continues on this side, red, red, red. It passes through orange, yellow, green, etc. So you see the continuous spectrum and all these dark bands. These dark bands we call nowadays Fraunhofer lines. And those are signatures of atoms and molecules in the outer atmosphere of the sun. So he didn't have an explanation for this. Fraunhofer turned out not to really be a scientist. He was an optician. He was more interested in making instruments than doing measurements and trying to understand things. An understanding for what these Fraunhofer lines actually were came in 1859 by two German scientists, Robert Bunsen and Gustav Kirchhoff, and they systematically investigated emission coming from heated elements, eventually leading them to discover two of the elements we know today, cesium and rubidium. Their apparatus looked something like this. This is the actual apparatus they used. This is a more refined version of it. But the idea is they had heated elements over here going through a prism and then observing the colors in a controlled fashion. Have any of you heard of Robert Bunsen before? Have you heard of the Bunsen burner? Often used in chemistry, but developed to do spectroscopy, right? Because it made a way to heat atoms or molecules, but not to give background light that would confuse the spectral signatures. So we're going to do a demonstration right now. Lidor is going to do a demonstration. We're going to heat various salts in a flame. What we're actually doing is we're going to put in each of 4 pans here. We're going to put in different salts. We're going to then put in a fuel to heat the salts. The fuel we're going to use is liquid methanol. We're going to light it on fire. The methanol provides a flame which is colorless. We heat the salts. We decompose them into their elemental forms. The elements get excited to different excited energy levels. And as they relax down, they will give out characteristic colors. Okay? And so we'll see this. We have 4 salts. We have lithium chloride, sodium chloride, strontium chloride, and copper chloride. The characteristic colors you'll see are coming from the sodium, the lithium, the strontium, the copper. These are very much the colors that you see in fireworks. Fireworks are nothing more than basically burning salts of various types. So we're putting in the salts. And then we're going to add to each of them the fuel. Don't do this at home, right? So we have one pan here where we have no salt at all, just the fuel. Why are we doing that? A control, right? We're going to show you what the flame looks like when you don't have any salt. We're really loading it up. Okay, and let's put the fuel far away. Okay, so let's light the control first. So you can see the control is burning with a, and I'm going to maybe try to turn off my screen here so you can see it better. It's burning with a light blue flame. Now let's light the others. So the last one is copper, characteristic green flame. The first one is lithium, nice red flame. Sodium, yellowish flame. And strontium, a reddish orange flame, right? And this is what Bunsen and Kirchhoff were studying. Where do these colors come from, right? These colors are coming from the various elements that are being heated and going to excited levels. And then when they relax back down, they give out this characteristic color. Those dark bands that Fraunhofer saw on the solar spectrum, right? Those dark bands are atoms in the outer atmosphere of the sun that instead of emitting, absorb the light that the sun has passing through it. And we'll talk about absorption and emission a little bit later. But very pretty colors. These are the source of fireworks, right? The colors you see in fireworks are nothing more than burning salts like this. And those are very nice. Okay, let us put them out now. Well, take a picture. And the key for Bunsen and Kirchhoff was to develop the Bunsen burner, because the only other light sources available before that were candles. And candles gave out a characteristic yellow flame coming from sodium. You couldn't get rid of it. So the Bunsen burner was key, not for necessarily chemistry, although we use it in chemistry, but key for the advancement of spectroscopy. Okay? All right, so now let's talk a little bit more quantitatively. Let's talk about where does this idea of spectroscopy come from? And let's thank Glador for and thank Paul. Sorry, Paul. Okay. So we have to talk a little more quantitatively. That means we have to talk about light. We have to talk about electromagnetic radiation. And our classical idea of electromagnetic radiation is oscillating electric or magnetic fields. So that's why light is often called electromagnetic or EM radiation. It is a wave phenomena, right? And a wave means that you have a localized disturbance that moves in space and time. If we've heard on the weather report, there's a cold wave in Boston, and by early next week it will move down to New Haven. Right? We all have in our mind what we're thinking about, right? We have a local cold disturbance in Boston. It's traveling in space and time, and sometime next week it'll arrive in New Haven, right? So a wave is a localized disturbance or a localized phenomenon that moves in space and time. What kind of waves are you very familiar with? Well, okay, sound waves, we hear that, but if you went to the beach, water waves, right? So these are clearly waves. These are waves generated by wind blowing on the surface of the water. Or what? Sorry? Animal waves? What? What? Sorry? Animals might push the water and make waves also. In fact, we can push the water and make waves too, right? So for example, this little movie shows taking an object and dipping it up and down in a pan of water and generating water waves going out from the source. So to generate water waves, I take my finger maybe, and I tap repeatedly in the water, and it makes the waves. If you want to generate electromagnetic waves, you take a charged particle and you oscillate it up and down. And it generates electromagnetic waves just like we can generate water waves here. But if you look at the edge here, you'll see that far away from the source, the waves look like oscillations. Up and down, up and down. So let's take a look at those oscillations. So here I have a wave amplitude, spatial position. So the wave has high points, which we call crests, and it has low points, which we call troughs. You can see we have many crests, many troughs. The separation between the crests is what we call the wavelength of the wave. The wavelength tells us the distance per oscillation of the wave. And if we're talking about light, the kind of electromagnetic radiation our eyes are accustomed to dealing with, well, green light has a wavelength of what is called in our kinds of units for spectroscopy, 500 nanometers. A nanometer is 10 to the minus 9 meters. This is a very small wavelength. To put that in perspective, a typical human hair has a diameter of 70 micrometers. So green light is 500 times 10 to the minus 9 meters. Typical human hair, 70 times 10 to the minus 6 meters. So typical wavelength of green light, blue-green light, is 140 times smaller than a human hair's diameter. So wavelength is one important property of light. Another, and that tells us something about the spatial properties of light. Another important property of light is its time dependence. So we want to think about timing a wave. So to time a wave, we might have a stopwatch, and we might want to count how many crests go by in a given amount of time. So, you know, we might turn the stopwatch when we hit this crest. That's crest 0, then we have crest 1, crest 2, crest 3, crest 4. We count as many as we want while counting how much time has passed. We divide how many waves have gone past by the time, and that gives us a quantity called the frequency, the number of oscillations per time. So for blue-green light, the frequency is very high. The conventional unit for frequency is known as the hertz, named after the person who discovered radio waves. 1 hertz is 1 oscillation per second. Optical light is measured in units of what are called terahertz. A terahertz is 10 to the 12th hertz. Or if 600 terahertz is blue-green light, so that's 600 with all of these zeros oscillations per second. So you mentioned sound waves, right? Sound waves in the middle of the hearing range for middle C, 256 hertz, as opposed to blue-green light, that's a factor of 10 to the 12th difference. Much, much higher frequency than sound waves. There is a fundamental relationship between frequency and wavelength. If you take frequency and multiply it by wavelength, well, frequency is oscillations per time. Wavelength is distance per oscillation. The oscillation factors cancel out, and you're left with distance per time, meters per second. Distance per time is speed or velocity. What speed or what velocity are we talking about here? It's the speed of light. The speed of light is about 3 times 10 to the 8th meters per second. If we want to put that in units that are more familiar for driving a car, this would be 186,000 miles per second, right? This is the fundamental speed limit of nature. As far as we know, right now, nothing can travel faster than that speed, right? But that speed is given, and this is the speed of light moving in a vacuum. When light passes through something that's not a vacuum, like a prism, it typically slows down and moves a bit slower than that. Okay. So this is the classical description of electromagnetic radiation. However, and it was all the rage, everyone believed it, until the turn of the last century, in 1900, when many experiments were performed that showed what Isaac Newton thought in 1666 wasn't so crazy after all. Under the right conditions, electromagnetic radiation behaves like a wave, but under some other conditions, electromagnetic radiation behaves like a particle. So this is the quantum mechanical or quantum description of light. light consists of localized bundles of energy, and those localized bundles of energy we now call photons. And that name was coined by the person I showed you, I think, on my second slide, G.N. Lewis, a physical chemist. Right? So light, under the right conditions, can behave like a wave. Under other conditions, it can behave like a particle. Right? We all have an idea of what a particle is like. Right? We'll agree that this ball is a particle. But modern science says that under the right conditions, this particle can behave like a wave. And waves can do interesting things. Waves can pass through things, right? Light passes through glass. Modern physical science also says we can be either particles or waves. It therefore says I can walk through the wall. There's not a high probability that I can walk through the wall, but it says I can. So modern science basically has what we call the wave-particle duality. Under the right conditions, something can be a wave. Under other conditions, it can be a particle. They're not independent. You have to combine the names together to get something that you might call a wavicle or a particycle. Okay? So that means light can behave like a particle, and we should be able to relate particle properties to wave properties. And there are two particle properties that I want to talk about. Only one is of real importance in spectroscopy. The first particle property is energy, the capacity to do work. The other particle property that's interesting is what is called momentum, the ability to give an impulse to something. If you want to think about momentum, right, if we have a big person running at a given speed, we say they have a large amount of momentum. If you have a smaller person running at that same speed, we say they have less momentum because we're thinking if they knock into us, the bigger person is going to have a bigger force directing us. So particle properties such as energy and momentum can be related to the wave properties. In particular, the energy of a particle is related to its characteristic frequency. So the energy of a photon is related to the frequency of the photon. The linear momentum of a photon is inversely related to the wavelength of the photon, where the proportionality constant is a fundamental constant of nature known as the Planck constant. Spectroscopy really cares about that energy idea because all of spectroscopy is nothing more than the conservation of energy. The amount of energy you put in has to be equal to the amount of energy you put out, you get out after you finish the process. We're not going to talk so much about this linear momentum, but that linear momentum could play a big part in the future. I encourage you all to do a Google search for solar sailing or light sailing, because in the future we might travel between the planets by using the fact that light coming in these little bundles has a linear momentum and therefore can exert a force. So instead of sailing with wind, we will sail with photons between the planets, perhaps. Okay, so we have an idea that light can be a wave, light can be a particle. Light has wavelengths, light has frequencies. I'm just going to show you now a depiction of what is called the electromagnetic spectrum. This is basically the wavelength and frequency dependence of electromagnetic radiation. So I'm trying to show you a part of the electromagnetic spectrum. Over here is wavelength in units of meters. Over here is frequency in units of hertz. There is no lower limit and no upper limit to the electromagnetic spectrum, but we tend to separate this electromagnetic spectrum into different regions. We have radio waves here, which have wavelengths on the order of a kilometer, the size of buildings. We have microwaves here, which are actually what is used in your microwave oven. We have the visible part of the spectrum here. On either side are less than visible, commonly called infrared, or more than visible. So this is less energy than red. This is more energy than blue, the ultraviolet. And then beyond the ultraviolet, very short wavelengths, X-rays and gamma rays. And I try to show you what the wavelength scale is over here, right? Radio waves, the scale of buildings. Microwaves, the scale of humans or butterflies. Infrared, we're talking about wavelengths on the order of a needle point. Visible, we're talking about little animals, protozoa, bacteria. Ultraviolet, we're talking about molecules, atoms that are joined together to form more complicated structures. X-rays and gamma rays, we're talking about atoms and atomic nuclei. Okay? And photon energy, right? The energy scales with increasing frequency, so photon energy is increasing here. Our eyes are sensitive only to what we call visible light. Visible light is this part of the spectrum, ranging from very blue, 400 nanometer light, to very red, 750 nanometer light. Young people can usually see a broader part of the spectrum than old people like myself. As you get older, your spectrum range decreases, so you don't see as far in the blue as a young person or as far in the red as a young person. So how does the electromagnetic spectrum relate to spectroscopy, to interacting with atoms and molecules? Again, it's energy conservation. So what are we talking about for spectra? In the case of spectra, we have energy levels in an atom or molecule. We have a lower lying energy level. We have a higher lying energy level. And then we apply light, which we can think of about as particles that have certain amounts of energy. If we want those particles to do anything with matter, we have to satisfy an energy conservation condition. We have to have that the difference in energy between these two states, E2 minus E1, has to be equal to the energy of the light that we apply. Otherwise, the light just passes through and does nothing at all. So this energy conservation criterion is what determines where a spectral feature appears. Because you have to have this HU21 equal to E2 minus E1. Therefore, where the spectral feature appears in frequency is just given by E2 minus E1 over H, which can be related to the wavelength like so. And so what does a spectrum show you? If you analyze a spectrum, and analyzing a spectrum is actually an art, because what you're trying to do is pattern recognition. Once you analyze a spectrum, you get a map of the energy levels in an atom or molecule. And if you know the energy levels in an atom or molecule, you know how that atom or molecule is put together. You know how that atom or molecule is interacting with its neighbors. So what kind of interactions can you have between light and matter? There are three basic processes, and these processes are at the heart of all spectroscopy. And I'll give you a demonstration of them in a moment. The first is what we would call stimulated or induced absorption. The idea here is that you start with your atom or molecule in a lower energy state. And let's understand, molecules and atoms prefer to be in lower energy states. You start with an atom or molecule in a lower energy state. You apply light or photons that have the right energy to satisfy that energy conservation criteria. It takes the atom or molecule and has it undergo a transition such that the photon is destroyed or annihilated. And by energy conservation, you're left with an atom or molecule in the excited energy level. That's the process that is of absorption. The photon gets destroyed, but energy conservation says that the molecule is moved from a lower energy state to a higher energy state. Another process that I'll demonstrate in a second is what is called emission, but this is spontaneous emission. We start with an atom or molecule in an excited state. Atom or molecules don't like to be in an excited state. They want to relax. They want to go back to a lower energy state. They can do that spontaneously by emitting a photon of the right frequency and falling back down to the ground state. This process of spontaneous emission often goes under other names. Other names are fluorescence or phosphorescence. The colors we saw from what the demonstration Lador was doing, those colors in the flames, they were fluorescence. Fluorescence is spontaneous emission that occurs very rapidly with high probability, high efficiency. Phosphorescence is spontaneous emission that occurs very slowly with low probability and low efficiency. And we're going to do a demonstration now showing you a little bit. I'll do that. Well, okay. Showing you a little bit about absorption and spontaneous emission. So what do we have here? We have here 5 different glass vessels. Oops. 5 glass vessels containing in water various dyes. Okay? And you can see the various dyes have different colors because you know, your light is able to sense which colors are being refracted or sent back to you. And now what we're going to do is we're going to pass different colors of light through these dyes. So we'll start with red. Okay? So red passing through this first cell. If you look there, and I don't know how well you can see, but it basically passes through with no absorption. Light just passes straight through, and you don't see very much in the wall of the vessel. So in this case, that red light doesn't have the right color to satisfy an energy conservation condition to give you either absorption or any kind of emission. Let's try a different color. Let's try green. So this is a very bright green. Our eyes are very sensitive to green light because the major part of light coming from our sun is green-yellow, right? So our eyes have evolved to be very sensitive to green-yellow. So let's take this green beam and pass it through. This green beam, when we pass it through, if you look, no light is coming out on this side. You can see that it is all being absorbed as it passes through. That green color is the right energy per photon to interact with the dye and get completely absorbed. Where that means when it's absorbed, it's taking dye molecules from a lower energy state and putting them in a higher energy state. What do they do once they get in the higher energy state? They relax. They relax by emitting light. And you can see the green beam comes in and yellow light is coming out the side. It's fluorescing down to various states in the dye molecule. Okay, so let's not use green. Let's instead use now blue. So this is a blue light source, about 457 nanometers. Blue, if we pass it through the first cuvette, you'll see that it passes through, so some is getting absorbed, but certainly not as much as the green beam. A lot is passing through. We go through the next. Here it is getting totally absorbed. Blue light is coming in. Green light, it's exciting the molecules to the excited level. And then fluorescence is coming out in the color green. Pass through this red cell here. Again, not absorbed completely. And clearly fluorescence, right? Some of it is absorbed, going to an excited level, and then coming back down and emitting. The next one. So again, most of it is going through, maybe a little sign of fluorescence, but not very much. And then the final one, going through, okay, but clearly being absorbed, right? Blue light is going through. Some of it is getting absorbed without a doubt. And you see fluorescence on the side, fluorescence in a different color. You put in energy of a photon of a given energy, the light coming out as fluorescence has to be either that energy or it could be less energy if there are other energy levels that it can decay down to. So what we see here is fluorescence. Fluorescence is something that, and we have here an ultraviolet lamp. You can see when we shine the lamp on the various dyes, it starts to glow because we're putting in enough energy to go to an excited state to have fluorescence occur. But the fluorescence stops as soon as we turn off the light source. Fluorescence is spontaneous emission that occurs very quickly with high efficiency. Let's now look at phosphorescence. So phosphorescence, I have here a piece of phosphorescent material. Now phosphorescent material, again, you have to put in enough energy per photon to go to an excited state so it can start to fluoresce. So let's start with red light, which has very low energy per photon. We shine red light on here, and now Zach will take his hand off. Nothing, right? Nothing. There's not enough energy per photon in the red light to go to an excited state to start to have... Oh. Okay. So let's do the red light again. Let's put it here, maybe. Red light again. Not enough energy per photon to do anything. So we don't go to the excited state. We have no emission in the form of either fluorescence or phosphorescence. Now let's use instead an ultraviolet. And we'll bathe Zach's hand. And then Zach will take his hand away. Phosphorescence. It'll last for a while, right? But eventually it will go back to being a dark screen completely. So fluorescence, and let's give an applause. So fluorescence and phosphorescence are both spontaneous emission. Fluorescence occurs very quickly with high efficiency. Phosphorescence occurs not so quickly with not so high efficiency. Oh, my laser pointer over there. Okay, so there are three basic processes. Let me turn this off and turn this off. We have stimulated absorption. We have spontaneous emission. The third process is the opposite of stimulated absorption, stimulated emission. Here we start with atoms or molecules in an excited state. We apply light of the right color to induce a transition. That light comes in and quote unquote tickles the molecule, causing it to fall down to a lower energy state. It emits a photon, but that first photon that started the process continues onward. So this is photon amplification. One photon goes in, two photons come out. It's more than that, however. It is photon cloning. The photon that comes out is an exact duplicate of the photon that came in. And this is the basis of the device we call a laser, right? Laser is an acronym. Each letter of the name stands for a different word. Laser is an acronym for light amplification by stimulated emission of radiation. Okay? So let's talk about spectra now. Let's look at the spectrum of atomic hydrogen. So the spectrum of atomic hydrogen that we're going to look at in a moment, we have an electrical discharge in hydrogen gas. We're going to pass it through a device that can take the discharge light and separate it into wavelengths. We saw that when we did that before with the white light, we got a continuous spectrum, right? All the colors of the rainbow. If you do this instead with a discharge in hydrogen, you don't get white light. You get these bands, which are often called spectral lines, only occurring at certain discrete points. So let's look at this now. We're going to turn on some discharge lamps and look at the spectra that we will see. And I guess what camera do I put here? Which one is it, sir? Auxiliary VGA. Okay, so the lamp that is on right now is a hydrogen lamp. You all have one of these diffraction gratings, I hope. If you want to use one of these diffraction gratings, you don't look directly at the source. Have the scale of wavelength towards your eye, and then look to the right of the source, and you'll see these colors. But I'm going to project these colors for you to see. So we're going to turn on a hydrogen discharge. Is it on?
It's nothing in here.
Oh.
I don't know if it's.
So we're going to turn on a hydrogen discharge. It glows red. And now we're going to project the spectrum. The spectrum that you get from that hydrogen discharge, not all the colors of the rainbow, discrete features, a red line, a blue line, a violet line. Just like you see over here, this is a fingerprint or barcode for atomic hydrogen, right? So this is the source, what spectroscopy is. By looking at the light coming out of that source, you can determine what is generating the light. In this case, this is the signature for hydrogen. If we switch to a different element, if we switch, for example, to helium, the spectral pattern is completely different. The lines are appearing in different places. We have yellow lines, green lines, blue lines, different from what we saw on hydrogen. It's a fingerprint, right? A fingerprint for helium. And finally, if we switch to a discharge of a molecule, we switch to a discharge of carbon dioxide, CO2, the spectrum now is again completely different. But also here, the lines are no longer sharp lines because a molecule has other things it can do. In particular, in a molecule, the atoms forming the molecules can vibrate with respect to each other. And that gives you a more complicated spectrum. So that spectrum has encoded in it a pattern. That pattern, in the case of atomic hydrogen, was analyzed at the beginning of the 1900s. The spectrum we saw for atomic hydrogen was this, the Balmer visible spectrum. It represents transitions occurring between sets of energy levels. And that tells us something about the structure of a hydrogen atom. Okay, so let's now talk a little about spectroscopy and lasers. And I like to give an analogy here. Spectroscopy before lasers in an analogy with communications, which is such an important part of our lives now. Spectroscopy before lasers was like this. I hope children still make this. This is a tin can telephone, right? Two tin cans with a string between them, speak in one end, sound gets transmitted by the string to a can on the other end. This is communication, right? But it's not very flexible, and you can't do it across country. That's for sure. That's sort of spectroscopy before the laser. Spectroscopy after the laser, totally different. We can do many, many different things. We can do them much more quickly, much more accurately, much better. And we can therefore learn a lot more about atoms and molecules by doing that. Let's understand some of the special Oh, how old is the laser? When was the laser invented? 70s is close. It was actually invented, oh, somebody else? 1960, exactly. This is the inventor. So in theory, it was proposed many years before, but in 1960, May 16th, 1960, this person at a research company, Hughes Research Laboratory, made the first laser, which he is holding in his hands. And what he is holding is this. He is holding a ruby rod. Ruby has chromium doped in a crystalline gem aluminum oxide matrix. Surrounding it is a flash lamp. That flash lamp is what excites the chromium atoms in ruby to an excited state. And then by doing the right things, by putting mirrors on either side, you can start to have a laser action occur. So it's very simple to make. Don't make it at home, right? But it was, at the time, a great discovery. Everybody agreed this was a great discovery. But very soon, everybody realized that, what do we do with this great discovery? It was called a solution in search of a problem. This has changed because now that laser has led to at least 8 Nobel Prizes in physics and chemistry. It's now a multi-billion-dollar industry, and it has become a solution for many problems. How many of you have a laser at home? Many of you probably do, right? If you have a DVD or CD device at home, the information on here is written with a laser, and it's read back with a laser. But let's talk about some of the special properties of laser light. So what's the first special property about laser light? It's monochromatic. It's single color. So if we, for example, look at the spectrum of solar light. So what I'm showing you is intensity versus wavelength. The yellow curve is the spectrum that you would see from a satellite above Earth's atmosphere. You can see it spans the visible part of the spectrum. It has ultraviolet. It has a lot of infrared. The blue curve is the spectrum you measure at sea level on the surface of the Earth, where the ultraviolet has been blocked out by ozone in the atmosphere, and we get these deep absorption bands coming from atmospheric gases like water, which is good, and carbon dioxide, which is bad, right? Global warming, right? But those are the absorptions you would see at sea level from various atmospheric gases. Even a run-of-the-mill laser, and this is a run-of-the-mill laser here. This is what is known as a helium neon laser. It produces a red beam of light, which I'm showing you on the door here. This laser has a spectral bandwidth that is a straight line on this plot. Extremely narrow band. And that way, if you want to do spectroscopy, you don't have broad sources of light. You have narrow band sources of light that you can tune through transitions and measure them very precisely. This is the basis of high-resolution spectroscopy. It is also the basis now of our time standards. Our definition of the second is based on transitions occurring in atoms and molecules. So the first property is it's highly monochromatic. The second property is it's highly coherent. And I like to show this picture, the light coming out of a laser, exactly the same color, all in phase. The light coming out of a conventional source, mismatch. I like to have the analogy, right? This is a precision marching band where everyone is marching in step and in phase. This is Yale's precision marching band, which is defined to be a scatter band, right, on purpose. But here we're marching stepwise, with the light coming out of a laser. Why is this useful? This is useful for something called interferometry. We take one beam of light, we break it into two, and recombine them after we've gone through different paths. What does this do? This gives us a process known as interference. So if we look at one of these movies of water waves, two water sources, now when they meet, this is interference. Where the water sources are positive, you have constructive interference. Where they're both negative, you have, again, constructive interference negative. But when one is positive and one is negative, they add together to give you a zero. So this is the phenomenon of interference. It provides a very precise way to measure differences in distance between these two arms. Why is that useful? There are two of these in our country right now. These are known as Laser Interferometry Gravity Wave Observatories, LIGO. This is the LIGO facility in Livingston, Louisiana. There's a similar one in Hanford, Washington. They consist of arms that are 4 kilometers long. They are trying to detect gravity waves. They succeeded just this year in detecting gravity waves, right? Gravity waves are the screams of dying stars. And the way you detect that is looking for very small differences in the arms of these interferometers. So laser light is very coherent. Laser light is highly directional, right? This laser pointer, stays a very small beam as I scan it over the ceiling of this room. Laser beams can stay highly collimated, highly directional, and this is useful for distance ranging, remote sensing, and even material ablation or material cutting. So many of us are familiar with radar, radio detection and ranging. It's what the police catch us with on I-95. Even better is LIDAR, light detection and ranging, right? Light detection and ranging is laser-based, shooting out laser at a car, seeing how long it takes for the beam to bounce back. Another way this is used is to measure distances. Every day throughout the United States at several places and throughout the world, we shoot pulses of light at the moon and time how long it takes for the light to reach the moon, reflect off, and bounce back. We do that to measure the distance to the moon. We do this repeatedly every day for years and years and years, and what we have discovered is that the moon is leaving us. Every year, the moon is getting on the order of 1.5 inches further away from us, and eventually the moon will depart from Earth, but it will be a long time. So it's used for distance detection. Another is high brightness. The sun, and this is a measure of intensity per frequency. The sun has a very low intensity per frequency. Run-of-the-mill helium neon laser like this beam, this red beam here, 13 orders of magnitude bigger. More powerful laser, even more orders of magnitude bigger. 20 orders of magnitude difference in spectral intensity. The most powerful lasers right now, petawatts, 10 to the 15 watts. To put that in perspective, the Millstone Nuclear Power Station in Connecticut, unit number 3, reactor number 3, has an output, a thermal output of 3.65 times 10 to the 9th watts. That's much, much smaller, orders of magnitude smaller than the power coming out of that laser. On the other hand, the Millstone power plant generates electrical power continuously. This laser is a pulse that is on for a brief part of a second. But during that brief instant in time, it puts out more energy than many power plants. So lasers can put out a lot of energy. You can do materials fabrication. You can certainly burn through steel plates very easily. The biggest lasers you'll find in the world are a place in Livermore, California, called the National Ignition Facility, where you have more than 192 laser beams that are being put into one place in one chamber, where they're trying to ignite something. It's not firewood. They're trying to ignite nuclear fusion. They're trying to ignite the power of the sun to provide a environmentally friendly source of power. Another property of laser light is that you can generate very short pulses. The shortest pulses of laser light right now that have been generated are on the order of 100 attoseconds. An attosecond is 10 to the minus 18 seconds. That's a 1 with 17 zeros in front of it and then a decimal point in front of that. This allows us to basically do stop-action photography, but ultra-fast stop-action photography. And one of the pioneers in this was Ahmed Zewail, who unfortunately passed away about 2 months ago. But this is the time scale that is now open to chemistry, running from milliseconds to nanoseconds to picoseconds to femtoseconds. Let's put this in perspective. Every day, hundreds of times a day, each of us blinks. How long does it take to blink? A second, if you blinked, if it took a second, we would call you doing a microsleep. It typically takes on the order of 50, a couple of hundred milliseconds, so 0.1 seconds to blink. This is 3 orders of magnitude smaller. This is another several orders of magnitude smaller. This is, you could say it's in a blink of an eye, but that would not be true. This is really, really short, so short that we can basically stop molecules when they're vibrating, stop molecules when they're rotating, and understand them completely. Understand their dances, their motions completely. I wanted to tell you a little about what we do in my lab, but I'll go through it very quickly. We're interested in fundamental chemical processes. A very simple chemical process, and one of the most common ones in chemistry and biology, is a proton or a hydrogen atom jumping back and forth between 2 sites, mediated by what is called a hydrogen bond, which isn't a real chemical bond, but is very much an electrostatic interaction. And to understand or to probe this, we are using some of the special properties of lasers. Lasers are so intense that you can have what are called multi-photon processes. Rather than one photon coming in, getting absorbed or emitted, you can simultaneously have multi-photons coming in and doing more complicated processes. And this shows diagrammatically what one of those processes might look like. Another thing we're doing in my laboratory is to understand molecular chirality. Molecules come in a right-handed form and a left-handed form. They're mirror images of each other. The 2 molecules that are mirror images have typically identical physical or chemical properties, unless you can put them in an environment that can distinguish handedness. And you don't have to look much further than your right or left hand to realize that biology is very much able to distinguish handedness, right hand from left hand. So light, it turns out, can also have this property of handedness. So we are interacting light that has right or left-handedness with molecules that have right or left-handedness to understand fundamental properties that distinguish a right-handed molecule from a left-handed molecule. And so my time is pretty much up. I wanted to just end with this, this final slide. Again, thanking my students for helping me to do all the demos here, and thanking you for your attention.